So we have studiously avoided the end behaviors of the transcendental functions up to this point. We've dealt with rational functions, which are a polynomial divided by a polynomial, and then the last example, which was kind of a tricky it's not technically a rational function, but it's very close. We kind of treat it like a rational function and kind of do some algebra tricks. But over here, we're dealing with transcendental functions. So trigonometric functions, logarithmic functions, and exponential functions, those ones. And we want to develop at least some patterns that we can spot. So the first thing we're going to look at is the exponential function negative 3 e to the x plus 2. So we want to describe the end behaviors of that function and sketch the graph associated for each. Okay, well, technically we don't know the rules for these yet, so we can't really do this analytically at this point, so we're just going to kind of look at the graphs and see what happens, which luckily for us, I have drawn already in Desmos right here. So this is the graph for part A right here. And it looks like that for negative 3 e to the x plus 2. So we can draw that graph on our paper, and you can see that as x goes to negative infinity, it's just going to slowly climb. Here, let me go over here. You can see it's going to 2. Now, Desmos says it is 2. It actually isn't 2. What happens is Desmos kind of gives up, like all computer programs will. So after a certain number of decimal places, in the case of Desmos 3, it just kind of rounds and calls it a day. But technically, these are like 1.99999, stuff like that. So 2 on the left, and then on the right, it's plummeting downward to negative infinity. We're going nowhere good fast. All right, so I will draw that graph on our paper right here. So we'll say, okay, I have y equals 2 as a horizontal line. If I can draw a horizontal line. There's y equals 2. That is my horizontal asymptote, excuse me. And then, oh, I can't remember where this thing intersects. Just below and just to the left. Okay, so kind of here and here. So I'm going to kind of swing it through like that. Okay, so over on the left-hand side, we can see that the limit as x goes to negative infinity is 2. That's that horizontal asymptote. And then over on the right-hand side, we're going nowhere good. So let me write that up. So the limit over here, on that negative side, the limit as x goes to negative infinity of negative 3 e to the x plus 2 is equal to 2. Okay. And then the limit as x, well, let me prove it to you analytically as well. Let me just show you something really quick. Since x is going to negative infinity, that would be the same as the limit as x goes to positive infinity, bear with me, of e to the negative x plus 2. There's no x on that one. See, I went from negative infinity with an x here to positive infinity, but with a negative x. I'm sneaky like that. And it's true, right? So imagine if it was negative 10, for example. Negative 3 e to the negative 10 is the same thing as negative 3 e to the negative, and then let it go to 10 here. But that would be the limit as x goes to infinity of, okay, that would be negative 3 divided by, remember, negative powers mean it needs to go to the denominator. And the denominator, once you move it down to the denominator, it no longer has a negative power. That's the definition of negative powers that we learned in algebra. But then this right here is 3, negative 3, divided by e to the infinity, right? What is e to the infinity? That's infinity, right? And 3 divided by infinity is a big fat 0. So this is actually 0 plus 2, which is 2. Sure enough, I proved it. There it is. That's an analytical proof right there. In case you want to see one. Over on the right-hand side, no such luck, because we're heading to positive infinity, so it's going nowhere good. You can see it right here. We're just plummeting downward. So the limit as x goes to infinity of negative 3 e to the x, sorry about that blob there, plus 2 would just be negative 3 e to the infinity plus 2, but negative 3 times infinity would be negative infinity plus 2, which is negative infinity. So sure enough, that one's going down to no man's land, going to negative infinity. Now, as for the absolute value of the natural log, that's a little strange. So let me pull that up. That's what I was trying to grab there. All right, so let me turn off part A and let me turn on part B. This is what the absolute value of the natural log looks like, believe it or not. It's a very odd graph. The absolute value is causing this little sharp point right here. Right? So if you just grab natural log, it has a negative values right here and positive right here. But then, matter of fact, I can show you natural log. Natural log of x looks like this right there. Oh, same color. That's not good to me. Let me make it red. Right? So there's natural log, but all these negative ones, because it's the absolute value, have been turned positive, and that's where you get that blue part right there. So that's strange. All right, so where is it heading? Well, as I get closer to 0, it's obviously heading to infinity, and it heads very, very fast. So fast that Desmos doesn't even really like dealing with it. It just kind of gives up very quickly. And then over on this side, it might seem like it's going somewhere, but it isn't. The natural log is just going to keep growing and growing and growing. And it may seem like it's going to 3, but there it is. I'll pass 3 right here. There's 4. It's slow, but it's just going to grow. So that means that both of those are actually infinity. All right, so now I need to copy those down onto my notes right here. And I just kind of drew a picture right there. I don't really have an analytical method for dealing with that because I'm just trying to learn something about how these transcendental functions work for this problem. But there we have it. Oh, so I should probably separate those, sorry. So that way it's a little bit more obvious that that part's B and that part's A. Okay, so that leads us to some end behavior ideas that we need to look at for exponential and logarithmic functions. And I've graphed them, sorry, that one's a little over there, I don't know why, but I've graphed them here. So let me turn off part B, and let me just do a general a to the x, which is the far left column of that table. And if I let a go to infinity, right, so I'm letting a get larger and larger and larger. So a to the x, if you want to see what I'm graphing, a to the x. So what you want to do is you want to think about what's happening as x goes to infinity, right? And a can be any number as long as it's greater than 0. Oops, I mean greater than 0. It says a has to be a positive number not equal to 1 that's greater than 0. So let me just make up something. There we go. Okay, so let me pick any number in here, it doesn't matter. But look at what all these functions have in common. As x goes to infinity, y goes to infinity as well. As x goes to negative infinity over here, y goes to 0. So looking back at our page right here, these ones look like, let me just draw you a graph real quick. They're all going to look something like this. Their steepness is going to get determined by a. Right? But then as x goes to infinity over here, let me do it right here. As x goes to infinity over here, the y is going to infinity. As x goes to 0 over here, or excuse me, as x goes to negative infinity, y is going to 0. Right there. Right? And this should look familiar to you because you learned this in algebra class. This is an exponential growth model. Right? Keep in mind for all of this that a has to be greater than 0. So a must be a positive number. Right? So if a is positive and real, right, not imaginary, but a is positive and real, and not equal to 1 because 1's no good to us, right? That would give you exponential growth, and that means that as as x goes to infinity, a to the x goes to infinity. As x goes to negative infinity, a to the x goes to 0. That is another way of defining exponential growth, if you will. Well, it's not defining, but it's a way of analyzing exponential growth. All right, now what if I look at a to the negative x? So let me go back. Oh, and then the a itself, all they're saying is it could be any number, and it just determines how steep, how steep this is right here. Like that. Okay, so then what about a to the negative x? Let me turn off a to the x. Let me turn on a to the negative x. All right, so a to the negative x looks like this. And that should also be looking familiar to you because that is exponential decay. I take it back. A should really be greater than 1. That's the way we should define this, but that's okay. So a is greater than 1. You can see it's exponential decay, right? So that's why over here it says, let me write this down, exponential decay. And it looks like this right here. And then as x goes to infinity, we're heading to 0 over here. But as x goes to negative infinity, we're heading to infinity. That's right up here. Right, so that's exponential decay. And again, I'm not happy with this up here. I'm going to change this. I'm just going to say a is greater than 1. It's a positive constant. It's more than positive though. It's actually greater than 1. Because if you get between 0 and 1, it's technically a fraction, which makes it a little strange. It'll make it, anyway, it'll make it weird. So let's just say it's greater than 1. It'll be, that makes me happier. Okay, so then logarithms. Okay, so the log base is back here. Let me turn off this one and turn on the general log. And this is what a logarithmic function looks like right here. And you can see, as x goes to infinity, this thing's going to keep growing. As x goes to 0, we don't go to negative infinity because, of course, you can't. You cannot take the log of 0, let alone the log of a negative. That's impossible. So we have the log of logarithmic function. Right, so a basic logarithmic function looks like this. It cannot actually cross the y-axis because we approach 0 from the positive side. That's right here. You can't take the log of 0. It's impossible. You can only take the log of a positive number. So I'm going to approach that from the positive side. So 0 from the positive side heads me to negative infinity right there. And then positive infinity as I approach infinity this way. So that's what a logarithmic function looks like. So these 6 rules are always true, right? As long as a is a is greater than 1 and constant. Let me just throw that in there. I don't like the word positive even being there. Let's just make a greater than 1 constant, then these will be true. All right.